Today, we finish up square roots by talking about adding and subtracting. I want to point out, because it's so tempting, to think that the square root of 4 plus the square root of 4 might be equal to the square root of 8. This is not true, and we can show this clearly because the square root of 4 is 2, the square root of 4 is 2, and 2 plus 2 is 4, and the square root of 8 is certainly not 4. This does not work. When we add square roots, we have to go back to algebra and the idea of adding like terms. We know that 7 plus 7 is 2 times 7. 7 and 7 are like terms, just like x plus x is 2 times x, because x and x are like terms. Then I can add the square root of 2 and the square root of 2. It is not the square root of 4. It is 2 times the square root of 2, or 2 root 2. In order to add square roots, they have to be like terms. If I had 3 root 5 plus 4 root 5, it would be just like having 3x plus 4x, which we know is 7x, and 3 root 5 plus 4 root 5 is 7 root 5. Keep in mind then, if I ask you to add root 2 and root 3, you can't do that. You could approximate it and come up with the decimal on the calculator, but these can't be added or simplified. This would be the answer if your answer had to be exact. It would be just like asking you to add x and y. We know x plus y is not xy. This is x plus y, that's x times y. I can't add x and y. They're not like terms. X plus y cannot be simplified any further. Adding and subtracting work the same way. So, if I said 8 root 3 minus 5 root 3, you just subtract the coefficients, 8 and 5. 8 minus 5 is 3, and you get 3 root 3. What we have to understand then is that we can only add square roots if they are like terms. That means if I ask you to add 7 root 8 and 4 root 2, you can't add them, except you can. You don't really know if you can add roots until you simplify the root. 8 has a perfect square in it. 4, 16, 25, 36, 49, 64. In fact, 8 is 4 times 2. I can take the square root of 4. It goes out front as a 2. There's multiplication right there. So this becomes 14 root 2 plus 4 root 2. They are like terms. 14 root 2 plus 4 root 2 is 18 root 2. Make sure before you conclude that you can't add them that you've simplified your roots, because it is true you can only add square roots if they are like terms. The rest of this video is questions from your assignment. If you have problems on a question, fast forward and you'll find an example just like the one on the assignment. Question 1. 6 root 3 plus 12 root 3. We think of this just like 6x plus 12x. 6x plus 12x would be 18x, and 6 root 3 plus 12 root 3 would be 18 root 3. 10 root 2 plus 5 root 2. This is just like 10x plus 5x, which would have been 15x. 10 root 2 plus 5 root 2 is 15 root 2. Question 5. Think of this like negative 8x plus 2x plus 6x, because it's exactly the same thing. I add my coefficients, negative 8, 2, and 6, and I get 0. This would be 0x, which is 0. Negative 8 root 5 plus 2 root 5 would be negative 6 root 5 plus 6 root 5. And those are opposites, and yes, they add to 0. Question 6. At first glance, we can't add these. They're not like terms. But maybe 108 has a perfect square in it. When I sum the digits, 1 plus 0 plus 8, I get 9. And 9 divides into 9. 9 will go into 108 evenly. Let's go over here and break that down. I'll take my calculator and I'll divide 108 by 9, and I get 12. Now remember our perfect squares: 4, 9, 16, 25, 36, 49, 64, and so on. 9 is on that list, so that's a good number. But the problem is 12 still has a perfect square in it. 4 divides into 12. 4 times 3. I can look and see then that my largest perfect square is going to be 4 times 9. When you multiply any two perfect squares, you get a larger perfect square. This then is 36 times 3. That's 108. I can simplify that because the square root of 36 is 6. I'll take it out in front and multiply. 6 times 8 is 48. 48 root 3 plus 10 root 3. Those are like terms. I can add them. That's 58 root 3. Question 7. I can't add these as they are because they're not like terms. But I look at 20, and I'm pretty sure that 20 has a perfect square in it. 4, 9, 16, 25. I don't have to go very far because 4 divides into 20. This is 4 times 5. The square root of 4 is 2. I take that 2 out front and I multiply. 2 times 5 is 10. 10 root 5 plus 4 root 5 is 14 root 5. Question 8. These are not like terms. They can't be added as they're written. But I think 98 has a perfect square in it. Perfect squares are 4, 9, 16, 25, 36, 49. In fact, half of 98, this is 2 times 49. So I'm going to rewrite this as 9 root 49 times 2 plus 4 root 2. Square root of 49 is 7. I take that 7 out front. There's times there, and I multiply. 7 times 9 is 63. Now they are like terms, and I can add them. 63 root 2 plus 4 root 2 is 67 root 2. Question 9. We have a subtraction question. And I'm pretty sure 36 divides into 360. I'll rewrite this as 36 times 10. 36 is a perfect square. Square root of 36 is 6. I'll take the 6 out front and multiply. I get negative 24 root 10 minus 7 root 10. Those are now like terms. I'll add my coefficients, negative 24 and negative 7. Negative 24 minus 7 is negative 31 root 10. Simplify the square root of 50. Let's list our perfect squares. 4, 9, 16, 25, 36. 25 divides evenly into 50. I'll rewrite 50 as 25 times 2. I can take the square root of 25. It goes outside as a 5. And 5 root 2 is the answer. Question 11. Think of your perfect squares. What's the first one that divides, the largest one that divides into 12? That would be 4. I'll rewrite 12 as 4 times 3. I'll take the square root of 4. It's 2. out front and multiply. 2 times 5 is 10, and my answer is 10 root 3. Question 13. Now I'm going to multiply these, and it's going to be 14 root 63. I took 2 times 7 to get 14, root 3 times root 21 to get root 63. I need to find the largest perfect square in 63. I want to point out that we can see the largest perfect square because the GCF of 3 and 21 is 3. They both have a 3 in them. They both divide evenly by 3. And when I multiply, I get 3 times 3 gives me a perfect square of 9. There's a 9 in 63. I'll rewrite this as 9 times 7. That's what 63 is. The square root of 9 goes out front as a 3, and there's times there. 3 times 14 is 42. 42 root 7 is the answer. Question 16. Root 5 squared is root 5 times root 5, which is the square root of 25. The square root of 25 is 5. The answer is 5. Question 17. 10 root 3 squared is 10 root 3 times 10 root 3, which is 100 root 9. The square root of 9 is 3. This is 100 times 3. Notice the root is gone. The square root of 9 is equal to 3. 3 times 100 is 300. The answer is 300. Question 18. Anytime you feel like it, if you have a fraction under a square root, you can split up that fraction. This is root 16 over root 49. The square root of 16 is 4. The square root of 49 is 7. 4/7 is the answer. Question 20. We need to simplify this fraction. 48 and 40 are both divisible by 8. If I divide 48 by 8, I get 6. Dividing 40 by 8, I get 5. Root 11 and root 77 are both divisible by root 11. I can divide them both by 11, and I get 7 and 1. Keep in mind the square root of 1 is 1. This will be 5 times 1 below, which is 5. Notice there's no root, because the square root of 1 was 1. 5 times 1 was 5. Up above, I get 6 root 7. Question 21. When we write an answer in simplest radical form, we usually don't leave square roots in the denominator. What we do is we create a perfect square. Take the root in the denominator and make a 1 with it. Root 10 over root 10 is 1. And when I multiply anything by 1, the value doesn't change. 1 times 10 is 10. It's still 10. Multiplying this by 1, it'll still be the same fraction. It'll just look different. This ends up being 20 root 10 over root 100. But I just made a perfect square. 10 times 10 is 100. The square root of 100 is 10. 20 root 10 over 10. Now keep in mind that when we cancel, for example, if I say 8 times 3 divided by 8, that's 24 divided by 8, which is 3. And if I cancel, I can see I still get 3. That works because I have multiplication. And that's what I have between that 20 and that root is multiplication. So I can cancel both of these. I divide them both by 10, and I get 1 and 2. This is 2 root 10 over 1. And anything divided by 1 is itself. 2 root 10 is the answer. Think about that for a moment. That means that 20 divided by root 10 is the same thing as 2 root 10. We would certainly rather use this instead of 20 divided by root 10. Question 22. When we rationalize the denominator, that means get rid of the square root in the denominator. The square root is irrational. We're going to rationalize that, make it an integer, a whole number. We multiply by 1. Take your root, multiply by 1. This makes a perfect square right here. This is 7 root 17 over root 17 squared. Now, I don't really need to multiply 17 times 17. It is 17 squared. And yes, 17 squared is 289. But when I take the square root of 17 squared, I'm going to get 17. Whether you make that the square root of 289 and make it 17, it doesn't matter. Up above, I have 7 root 17 over 17. Nothing cancels. There's no common factors. This, then, is my answer. Question 23. Anytime you feel like it, if you have a fraction under a root, you can split up that fraction and make it into 2 roots. Root 5 over root 13 is the same thing. We don't leave roots in the denominator. We'll multiply by 1. Root 13 over root 13. This creates a perfect square there. This is root 65 over root 169. Now, I didn't need to multiply 13 times 13. I could have just written that as root 13 squared, which is going to be 13. The square root of 169 is 13, just like root 13 squared is 13. My answer then is the square root of 65 over 13. Question 24, the last example, is Pythagorean theorem. Remember, we say a squared plus b squared equals c squared, where c is the hypotenuse, always opposite the right angle. We know that a and b, they can be interchanged. I can make them b and a, it doesn't matter. That means I'm going to get x squared plus 12 squared equals 14 squared. That's x squared plus 144 equals 196. Let's take 144 from each side and get that x squared by itself. 196 minus 144 is 52. I'll take the square root of both sides. And this simplifies. There is a perfect square in there. 4, 9, 16, 25, 36. I think 4 divides into 52. It's 4 times 13. I can take the square root of 4 out front. It goes out as a 2. My answer then is 2 root 13.